Good afternoon, everybody. I'd like to welcome you to this talk on federating OpenStack-powered supercomputers. My name is John Garbett. My IRC nick and Twitter handle is John the Tuber Guy. Just to prove that that isn't completely made up, given that the keynote was full of people playing music, I figured I should try and make clear that I do play the tuba. It's not just a made-up name. Well, it is a made-up name, but it's for a reason. This is me with my brass quintet. So today, so back in December 2010 is when I started working on OpenStack, but for the last 18 months or so, I've been at Stack HPC, focusing on sort of scientific computing and OpenStack and how those things all interact. But today I want to focus on this idea of federating a supercomputer. So let's start with some context. This is all part of a project called IRIS, aiming to build e-infrastructure for STFC science. So for context, the STFC is a research council within the UK. It's the Science and Technology Facilities Council. What that means is they're responsible for the big scientific facilities that are sort of national infrastructures within the UK, things such as the Diamond Light Source and various other kind of different big scientific facilities within the UK. They're also responsible for lots of the UK's participation in international efforts, such as the participation within CERN, within the Square Kilometre Array, and similar things like that. And what happened with IRIS is that STFC looked across all of their different projects, and there was a big shortfall in the compute resources required to do the science. Lots of the equipment's being upgraded, the data rates are increasing, therefore the compute needs have been increasing. And I wanted to look at how to do this, more efficiently between these different groups. At the same time, the background here is that within the UK, there's a push to stop giving capital grants for infrastructure dedicated to particular projects, so you don't get this siloing effect, and trying to look to build a UK-wide e-infrastructure for science. So STFC have got this pot of funding for capital assets to look at what STFC as a community needs together for that kind of UK-wide infrastructure to work for them. A big part of this project has turned out to be community building. It's interesting sort of following on from my experience working with OpenStack and seeing the communities come together, people realizing they're trying to do the same thing and share efforts. It's been interesting seeing this work within the IRIS context. So the simple example is lots of people are trying to do Jupyter hubs. And they're all getting together and saying, well, let's try and do this in a similar kind of way so we can start sharing the infrastructure more dynamically. But more on that later. So in this slide, I've made the bold attempt to summarize the whole of scientific computing and all of their needs into a small flow diagram. Clearly, I'm missing almost everything, but there's some interesting observations here. So to walk through this diagram, I'll first look at the example I mentioned of the Diamond Light Source. So what typically happens there is someone might bring a sample of like some particular new metal they want to have a look at, and they need to shine the light on that and have a look and understand the properties of that material. So that's where you start with the green experiment box. That produces a whole bunch of data, and that needs to get to something the scientists can use. In this particular case, they're interested in having real-time visualizations of what's going on. So in real time, they need to look at what's happening so that they can decide what the next experiment is. I say in real time, I mean in some sensible turnaround time. So these scientists have flown from wherever they live across the world or within the UK, and they come to the facility for a certain scheduled period of time, and their concern is to make the best use of that time. So that's one set of requirements. If we take another sort of user group or another project that's kind of trying to use some parts of this, we could take the Square Kilometre Array project, and in particular, how the science data processor from the Square Kilometre Array interacts with the science regional centers. So let me give a bit of context. In this case, you've got telescopes producing this spew of data coming in from the green box. This data you want to try and collect it, because it's just on the network, you need to get it to collect it. You need to reduce it down to a set of images of the sky. These images then get sent to regional centers where you can actually process them and work out what the images are and what's interesting. So here we've got locality of the compute is actually defined by that data pipe that's coming from the green box. So you've got that blue section has to be sort of near that green box, but the red side is more flexible. If that sounds familiar to you, it's probably because you've heard someone talk about the CERN system and how their grid system works. It's exactly the same kind of principle. You try and get the results that you can then send out to your tier 1 centers, and they do a very similar kind of set of things. So let's try and extract some interesting information from that. How can we generalize this? Well, if you look at the requirements in the compute, there's an element of what. So what I mean by that is, what the request is. So firstly, scale. One side of the equation, some of these simulations require MPI style, lots of machines working together with a sort of low latency interconnect to make progress. On some other sides, and they're doing more sort of high, so that's the high performance computing typically, it's labeled as, and sometimes it's high throughput where you may even have single CPU jobs they're trying to spin over the whole cloud. So depending on the context, there's different requests for that. That can dictate different hardware. If you look deeper into the job, some of these jobs need large amounts of memory, some need shared file systems that are fast. Some of them are doing FFTs where it makes sense to get it to the GPU. And there's a whole slew of different requirements that choose the different hardware. On the other side of things, I mentioned that need for locality between the data feed. That obviously can dictate exactly where you need to run this thing. Another axis to look at is when. So batch job submissions are still quite common, and it really helps with trying to load balance between all the different requirements, particularly when you try and deal with some of the interactive workloads. People have got access to a physical facility and need to get that processing done. So sometimes you just have to do it there and then. And one of the problems that some HPC facilities are having right now is there's an awful lot of demand for web services like Jupyter Hub, whereas the typical batch system is struggling to deal with those needs. So if we take that world of requests that we're getting from all these different users within STFC, the observation here is that there's lots of resource sharing opportunities due to this diversity of request. So firstly, I mentioned already about facilities. They've got demand spikes, so when the beamline isn't working, that resource can be used for other things. When there isn't a scientist on the site, again, that interactive processing can be used for other things. If we look at the shared HPC cluster, and you look at the typical demand and availability, you kind of see a sawtooth of availability. So when you expand the HPC cluster, you have these chunks of extra capacity come online. Generally, that extra capacity has been justified because the previous machine was full, and all the batch queues were getting very far behind. But if we could stagger these across different sites, we might better be able to bring online a new facility and spread the resource over more places as we stagger the procurement. So there's definitely a resource sharing opportunity in the fact that some sites have too much demand and some sites aren't yet filling their new machines because of the existing user base isn't yet being able to make use of all the resources. And you have very similar situations when you start dedicating resources. So what's one way this is done today? So today, the typical deployments are actually very siloed. So a particular site and a particular set of hardware is very often destined and has been bought for a particular purpose. So it's quite static, it's quite common. So we have shared clusters that are just running, are accessed via batch systems, and you've got the grid sites and other sites where to access those resources, you need to use that particular platform. So if we look from the science user point of view, if their GPUs are only available in the batch cluster, and if their single node, well, their single CPU jobs are only available via grid, they're sort of forced to choose the platform not that best fits their workflow, but that fits the hardware availability. And if the mix between the demand for these particular types of compute varies between the platforms, it's quite hard to decide what to do. So what we found as an OpenStack community is that OpenStack is quite a good way to break this silo. It gives you somewhat of an independent way of delivering the infrastructure versus delivering these platforms to the scientists. One of the big observations here is the bare metal deployments from Ironic. That can actually make quite a big difference on the number of workloads you can support. Now, there's a thought experiment that I like to think, that I like to tell people about this who aren't sure about Ironic. Let's take one of these batch clusters and imagine we have this super MD5 function that takes the whole of the batch cluster and gives you a number. Now let's take another system deployed by Ironic and do the same thing. Theoretically, we can make those match. Ironic gives you exactly the same thing, except it's now got using software-defined infrastructure techniques. I say it gives you the same thing. You'll probably find it's totally different because all the different configurations and all the different nodes that have been hand-changed, you don't need that anymore because the Ansible will make it more consistent. But you could make them absolutely identical. That's the idea. The other piece to note here is that the multiple sites are exposing their special capabilities through OpenStack flavors. So your set of OpenStack flavors can say, these VMs, over here you can have machines with very large amounts of memory to core ratios. Over here you've got your GPUs, and we can use OpenStack to describe that through the flavors. So if we zoom out of that previous picture and try and generalize this, you get this, at least in an idealist world, you get this nice layering of different pieces. We have the OpenStack layer at the bottom that gives you access to your infrastructure. And importantly, this can be run by a completely different team to the person that's running the platform. So now you have teams dedicated with the platform that aren't tied to the particular sites necessarily. You've broken that dependency between the platform, the people running the platform, and the people running the infrastructure. The other piece here, I think, which is important to note, is this idea of sharing between these different layers. So here, I've tried to represent the fact that the scientists may want to directly use OpenStack to set up a completely custom stack. But that's probably a very small number of scientists that are looking at doing that. Generally, people are accessing the platform that they're accessing today, but on new infrastructure or a new platform built. But the idea here is that you can try and share more and more as you go from this different layer of the stack. So the scientists, necessarily, their workflows are specific to their code or their particular set of parameters. But as you go to the platform layer, people can start reusing all of that software-defined infrastructure that defines how your Slurm cluster might work or how your Jupyter Hub works. So those platforms can be shared between the different scientists. Also, those platforms can be customized to particular use cases, which is also interesting. But the further you get down to the green layer, that's sharing between all of these different people. An example of the services I'm talking about here is Kubernetes. So there's an awful lot of things now building on Kubernetes. And here we can deliver Kubernetes using OpenStack Magnum that's tightly integrated with the infrastructure as a service tier. So at this point, you're saying, that's all very interesting, but he hasn't really talking about federation yet. So let's redraw that picture with a federation mind point. So the very astute of you will have noticed that the green box at the very bottom has now got 2 bits. So what I'm trying to represent with this is that we've got multiple OpenStack sites all available to all of these platforms and the services. Let's ignore the AAA piece for a moment and concentrate on that infrastructure as a service having multiple pieces. In recent years, the OpenStack community has made great strides in ensuring that different OpenStack deployments are interoperable. One of the ways they've driven this forward is through the OpenStack interoperability tests. And what we've done with Iris is to reuse those tests to try and get a set of tests that say, is this OpenStack cloud usable as an Iris-style OpenStack cloud? Now, the idea of the tests is that if you restrict your usage of the OpenStack APIs to the APIs that are validated by the tests, any script using that subset will work across any site that uses the Iris compliance tests. The interesting piece here is when you look towards the hybrid model, it would mean that you can actually use the same set of tests to say, is this OpenStack public cloud a valid Iris site? Now, I'm hand-waving across the AAAI piece here because I'm ignoring that. But that's an interesting use. And that's also one reason why we've built this on the OpenStack interoperability tests. The idea here is that any of the required tests that are defined for Iris compliant tests will pass on any OpenStack certified cloud, which is a really powerful model. So any cloud with the OpenStack certified logo, these tests should pass on. So when talking with the scientists about this model, they get very excited about the idea of this location transparency. And what I mean by that is they want to write their code in such a way that it just uses the best infrastructure in the ether to do the right thing. With that in mind, people come back and look at OpenStack and say, well, it's interesting, isn't it, how you have a different API endpoint for each region. How do you deal with this disparity? The way I like to think about that is if we think back to that layering diagram that I've been through several times, it's important, I think, for the OpenStack layer to be very explicit about where your infrastructure is. You can say that the layers building on top of that need to know that the data and the compute are in the same kind of place. They need to know that that's how the network is laid out. But it's the platforms built on that that give you the location transparency. Okay, so what is AAAI? Where's this big green box on the left-hand side? Problem solved. Woo! So I just want to give some context here. I'm going to focus on how do we get authentication, authorization, and accounting done for the OpenStack green layer. So that's where the 3 A's come from. The long-term vision is that this single AAAI system can be used for both the platforms and potentially the scientists above. So what I mean by that is when you log into Jupyter Hub, it'd be great if the same authentication system is used between all the different instances to try and manage this as one piece. So there's more sharing again. There's a bit more work to do there, but let's focus on the OpenStack side of things. So the authentication authorization, in the simplest sense, what we're meaning here is that all of these scientists that are participating in an STFC project belong to a particular organization, usually a university. So they have credentials already that they're using to access their usual work things. And we'd like them to use those exact same credentials and login screen to access OpenStack. And this is possible using Federation. An additional complexity here comes to policy. So we're actually using Keycloak to make sure that any user that's logging in is accepting the correct policy for the particular site that they're authenticating to. Long term, the Iris project wants to have a harmonized acceptable use policy, so you can accept that once within the whole federation. But right now, it's individual for individual sites. And the idea is that you want to request access to the project, and then the project owner will allow you access so that eventually you log in with your usual credentials and you see the project that you've been given access to. That's the overall story. One thing that's new here is we've actually made use of app credentials within Keystone. This was added in the Queen's release and is definitely very usable and rocky. What this allows you to do is to access Horizon using that same system, and you can create credentials that you can actually then use in your scripts. This is important if we're trying to tell people to embrace this software-defined infrastructure way. We don't want users having to click buttons to deploy infrastructure. We want their scripts to do this for them. And app credentials is a way that you can create specific credentials that are individually revocable for your scripts to do what you need. This is more important in the federation case because you don't want to have to pop up a web browser or do something like that to actually get your script started. You need to have that chaining. When I said I'm only covering the OpenStack piece, ideally this would be something that would work for all layers of that stack. Right now it only works for services that are protected by Keystone in this model. So how do we build this? What's the building blocks? So one of the key building blocks that we've been using is OpenID Connect. The basic idea here is that once you've authenticated to the university, there's a system, a proxy, that maps you to a unique user, and the unique user is communicated to Keystone through OpenID Connect. Essentially, Keystone gets handed a dictionary of loads of interesting properties, and Keystone can do some fun things with those properties. In terms of Keystone doing fun things, that's where the federation mapping comes in. What the federation mapping says is, if you're logging in with this particular bit of your this particular key, then this key can create your username, creates your email address. And so you can do the mapping to automatically create users and roles on demand. Now, earlier today, there was a session where we were actually talking in the forum about how to improve this, and I was telling the people in the room and the Keystone developers in the room about the particular use case we have here. But one of the limitations is we can't use group mappings, not to go into why that's particularly interesting right now, but there's work to actively make this more flexible. I like complicated diagrams, so I thought I'd add another one here. But really what I'm trying to show are the different components involved. So we've got OpenStack services, and we've got other things protected by Keystone, which might be Ceph Rados Gateway. So your object store might be also protected by Keystone. When you log into Keystone, it might redirect you to something like Keycloak, which in turn might redirect you to something like EDI check-in. But the important piece is that Keystone gets those credentials via OpenID, gets that dictionary of properties from OpenID Connect that assert what the user has, and the federation mapping creates the appropriate permissions that you can get into the system, and also creates them in such a way that app credentials work. Could probably spend 4 hours describing this diagram, but I think the interesting thing to note here is where passwords live. The important thing here is that the user's password is only known to the university's identity system, whatever it may be. Keystone does not know what the user's password is. So all Keystone gets are the set of properties that we trust to be correctly given to us from the chain of proxying. Now, the academic community has done an awful lot of work on describing the system. This is apparently about to be out of date from AARC. This is a European project. The European project has gone into a lot of detail about how you actually make these trust systems work. I'm not going to go into that detail, mostly because I don't know the detail. Let's talk quickly about accounting. The focus we had for Iris, and generally following the focus from most of the similar kind of science projects, is to worry about traceability. So let's be clear what we're not worrying about here. If this was patient identifiable data, we're really worried that bad actors are going to do something bad. What we're doing here is that if there happen to be bad actors, we know what they did. So that's what I mean by traceability. So we're just making sure that we know exactly what happened. So if your network administrator comes to you and say that we've seen bit mining activity from this floating IP address, you kind of want to know who was doing something with that floating IP address. That's what we mean by traceability. For Iris, what we're actually using is you're reusing the EGI Apple system. Partly this is because the developers behind this system are employed by STFC, so that's very convenient. We know that they can make it work how we want, because they said they would. But the basic idea here is you query OpenStack using this CASO tool, I call it Caso. I don't think the developer calls it that. But that tool scrapes OpenStack APIs and then gives you the records for the other system to do its good work. We're using quota here to limit the maximum concurrent usage. I was very careful with those words. We want to give people CPU hours in a sort of HPC kind of way, but right now we're just really limiting the concurrent usage levels within a particular month by updating quotas. And just, there's a smaller number of users, so we're not worrying about that too much. Okay, so I mentioned that to get that multiple green layer working, this green infrastructure as a service layer is modeled by these compliance tests. So as a deployer of these particular systems, how do we get these compliance, how do we pass these compliance tests? So what we've done is we've worked to try and build reusable operational tooling. I'll go into the building blocks of that. But the basic idea is that we can actually create a digital asset using the capital funds. So this Iris project was all capital money, so there was actually no money for operating the system. It's just the realities of trying to get funding from government. It turns out you can create software to help the operators, and that's an asset that depreciates over time. So the key thing here is to try and build this OpenStack distribution. You can take this distribution, apply your site-specific configuration, then you get the Iris tests passing. That's the idea. How do we do the OpenStack deployment? Well, the tool of choice for this particular community has been OpenStack KOB. What that really means is you're using Ansible and containers to deploy your OpenStack. So it reuses, it is an upstream component itself, but it's reusing OpenStack Collar images, and it's using Collar Ansible to configure those images, but it tries to get all the missing pieces so you get from bare metal to an OpenStack cloud. So how do we install Ironic? Or how do we install the operating system? We're installing the operating system using Ironic. In this case, we're actually using the Bifrost packaging. So there's a standalone Ironic deployment used to deploy the control plane. So your controllers are deployed by Ironic, and the hypervisor is deployed by Ironic. And then on that, we've got some Ansible to make sure that we set up those operating systems such that Collar Ansible can do its work. So KOB is the piece that actually glues this all together. So I'd say one of the biggest challenges when deciding where your workload runs is storage. I haven't really spoken much about storage today, but I wanted to go through the choices that this particular configuration has made. So firstly, for VMs, generally speaking, the system is trying to give VMs to use local disk by default. So the default ephemeral disk for VMs is the local disk. This is particularly chosen because the compute nodes we're targeting for this deployment generally have SSDs, and we want to allow that performance straight through to whatever system's running in the VMs. This has worked rather well, but some VMs will need a lot more storage than that, and we're offering cinder block storage to add that in the standard way. On the Kubernetes side of things, there's an awful lot of requests for this Jupyter Hub system. Jupyter Hub is actually using the persistent volumes in Kubernetes when you deploy it with Helm to store the user data. Now, this means that this persistent volume ideally is in the multiple reader, multiple writer attachment across multiple machines. Now, how we're actually doing that is we're using the OpenStack cloud provider within Kubernetes to integrate Manila-defined CephFS shares. So I just said a whole load of words there. Let me try backtrack a little second. So with OpenStack Manila, it can basically carve up a file system and set permissions on demand. It also sets quotas on those file systems. I'm ignoring the fact that until you use a very recent version of the kernel, it ignores the quota, but let's just skip over that for now. So Manila gives you a file system of the right size with the right permissions. The cloud provider OpenStack bit means that when you request the persistent volume in Kubernetes, this can be automatically or defined to a particular Manila share. So the size of your volume can just be passed through to Manila. this has proved a really nice way of getting this all working and pretty performant. The other piece I touched on was Rados Gateway. The idea here is to use Keystone protected Rados Gateway in the hope that we can make good use of the application credentials and all of the federation stack to get that all working together. Right now, that's a little bit of work in progress, so I can't talk about the details of that section. So, any unsolved problems? Well, actually loads, but let's just highlight a few that I think are interesting, things that we can work on next. When I went through this slide previously, I was waving my hands around a lot, which you probably noticed. What we'd really like is to use something like Keycloak's group management system so that users have a nice user interface to say, I want to request access to this project, and the owner of that project can authorize them, or the reverse of that, where an owner of a project invites a user into the group to make use of those resources. So this is very similar to the VOM system that's quite popular right now, well, popular in the grid systems. And getting this fully integrated has proved quite hard work and just isn't there yet. I mentioned that the AAAI system is hoped to be shared between all of these different levels of the stack. Now, there's a really interesting group of people that have been getting together called Federated Identity Management for Research, which FIM4R for short. Now, the quote here I just thought was really interesting because I think they're taking exactly the right direction, is basically don't get in the way, is what this quote is trying to say. We want the system to just work and enable the scientists to do what they need to do. But if you go look at this report, they've actually looked at what all the requirements are needed from a good federated identity management system for all those different layers of the stack. And there's an awful lot of coalescing around some of the needs now. I think that's some really interesting work on where to go next with making sure that all those different bits of the stack work together nicely. I think that this particular idea will be really effective once we get things like preemptible and spot instances working within the system, along with reservations from Blazar, along with quotas and everything else. When we can get this all working together, I think it will be a really powerful system. So Blazar, if you've not heard about it, is a project where you can try and request some amount of compute resource at a time in the future and schedule that. That's a really nice fit for that work, the case where the user is known to come to the system and wants an interactive workload at some point in the future. You can sort of fill up your calendar with all of these reservations. Now, the piece that isn't quite working yet, but I hope won't be too far away, is that for right now, Blazar, you basically has to own some subset of your cloud and only allows reserved instances in there, as in instances that have already got a reservation slot for the future. The hope is that you can actually get the opportunistic resource to use that resource in the meantime to fill in all those resource gaps. So when that's working nicely, this should give us quite a good layer to actually mix those together. The other piece, I've put operations in here. What I'm really hinting to is that if you've got some spare capacity within the system, you can actually do some live migrations. So when we were a lot of the hard work here is choosing a specific OpenStack configuration that meets both the performance needs and the operation needs. One of the key tenets here that we wanted to make sure was that we could actually shuffle all the VMs together to free up space so that you can actually then convert hypervisors to bare metal and vice versa to try and get more of this resource sharing. That's why the operational bit is in there. So how would I summarize the lessons learned from this whole activity? So the first thing, I think, is that building a community matters. Getting this relationship between the people that are all doing the same kind of platforms, all doing the same kind of things and talking together. If the scientists don't believe in the system, it won't get adopted and the system is dead. But the building community has been really interesting and seeing lots of good work starting to come out of that. Federated OpenStack works. So this system of having multiple OpenStack sites, exposing the different capabilities, and federating, the federation system, it does seem to work. It's not just make-believe. If you look at some of the blueprints towards edge computing use cases, the use cases between the scientific community doing this kind of sharing of resource and the edge computing use cases, they're very similar technical challenges that they're trying to meet. Completely different reasons for their use, for the challenges that they're facing, but you've got these very similar challenges of multiple sites working together. And there's been some of the, certainly some of the discussions in the OpenStack forum and PTGs has proven really useful to sort of collect all these different varying use cases from very different environments, but basically the same technology will fix both of our problems. The third thing is, and it's with a qualifier, is application credentials can work. There's still some work to do when you're using group role assignments, and that work is in progress. If you've got concrete role assignments, the application credentials do seem to be working really well to get that non-interactive user. Even if you're in a much simpler OpenStack setting where you've got an LDAP system locally that you're integrating your Keystone with, but you don't want those LDAP credentials to be used, application credentials are really useful there in the same kind of way. So, I'd like to thank you very much and for listening and ask for any questions, if there's any questions. I believe we have a microphone for questions. Well, people can shout out and I can repeat the question if you don't want to walk to the microphone. I'm happy with that too. No one going first. Okay, well, I'll say thank you very much for listening. Oh, yeah, thank you very much for listening, and I'll stay around here for some questions in the meantime. Yeah, so thank you very much.